M-ary trees are in fact rooted tree with a parameter m. So how to find the parameter m? Now for any rooted tree, we have two types of vertices. Either it is a leaf or it is an internal vertex. Any vertex that has children, including the root, is internal vertex. Otherwise, it's a leaf. So how to find the parameter m? You count the number of children for each internal vertex. The one with the maximum number of children, we will use its number of children as the parameter m. Next, the tree is full if every internal vertex has exactly m children. For M-ary tree, if m is equal to 2, then the rooted tree is called a binary tree. When we say that the tree is balanced and when we say that the tree is complete, we say that the tree is balanced if all leaves are at level h or h minus 1. Remember, h is the height. So also from the word balanced, what does it mean? It means when you look at the tree, when you draw it, it should not be drawn like it looks like it's going on one side. So how to verify that it is balanced? Find the height and check for every leaf, it should be at h or h minus 1. For complete, first of all, it should be full, and then every leaf should be at the same level. For some examples, the first example here, first I need to find what is m, and m is 2. And how did I find m? By counting number of children for each internal vertex, and all of them is equal to 2. So m is equal to 2, at the same time it is full, because all internal vertices have the same number of children. Now why it is not balanced? We need to find the height. Now the height is, the maximum level is 3, so the height is 3, and h minus 1 is equal to 2. Well, now we need to check every leaf. Now this leaf is at level 1. It's not at level 3, it's not level 2, so this is why it is not balanced. And as if you look at the tree, it is going on one side, which is going on to the left side. For the next tree, we need to find the value of m. So we need to count the number of children for each internal vertex, starting from the root. So the root has 3, b has 2 children, c has 2 children, and d has 2 children. So m is the maximum, which is equal to 3. Now it is not full. Why it is not full? Because not every internal vertex has number of children equal to 3. Now why it is balanced? Because every vertex is at the same level, and this level, which is the height, is equal to 2. Why it is not complete? Because it is not full. If it is full, then it will be complete because every leaf is at the same level. For the last tree, rooted tree, it is obvious that m is equal to 2 because every internal vertex has number of children 2, and it is full because all of them number of children is equal to 2. It is balanced because all leaves are at the same level, which is at level 2, and it is complete because it is full and all leaves are at the same level. So if all leaves are at the same level, it makes it balanced, but not necessarily makes it complete. An example is here. All of them are at the same level, but it is not complete. For M-ary tree, we have the parameter m. And now we would like to show you what is the relationship between m and number of vertices n, and number of internal vertices, and number of leaves if the M-ary tree is full. So for part I, if you know m and you know n, then you can find I and L from these equations. Number 2, if you know m and you know I, then you can find n and you can find L using these equations. And if you know m and you know number of leaves, then you can find number of vertices using this equation, number of internal vertices using this equation. We will show you that you need to remember only 2 equations that gives a relationship between these 4 parameters. And from these 2 equations, you can deduce all of these equations. Let us find these 2 equations first, and then we will come back to show you how to find these other equations. Consider the following full 3-ary tree. So m is equal to 3. And now we need to find the other parameters I, and you can count I from the tree, it's equal to 5. And also we know that n is equal to L plus I, because for M-ary tree, the vertices are either internal or leaves. Now, can we find n from number of internal vertices? The answer is yes. How? See, now this is an internal, since every internal vertex has 3 children, so we can start that by saying we're counting their children, so we will say that we have 3i. So for this internal vertex, we count their children, its children, and it will be 3. Now for this, it's already counted by its parent. We are going to count its children, so we will count these vertices. This vertex is already counted by its parent, so we are going to count its children, and etc. This can be applied on all internal vertices by counting their children, except the root. We did not count it. We have counted its children in the beginning, but the root was not counted, so this is why we have to include it in the equation. And now we have n equal to 3i plus 1. We can generalize this because this equation, or these equations, when m is equal to 3. And we would like to find what is n and what is I and what is L. So these are the 2 equations that you need to remember. First is that n is equal to mi plus 1. And the second one is that n is equal to L plus I. From these 2 equations, if you know m and you know I, then you can find n and you can find L. If you know m and you know n, you can find I and you can find L, and etc. And this is what was the theorem about in the slide. Now let us go now back to the theorem and try to show you how to find those equations from only these 2 equations. And remember that we have full M-ary tree. So let us find the equations for part number 1. For part number 1, here we need to write that given m and n. So we have to start by saying that m is given and n. So the equation for the other part, here we will say find I and L, the equation for I and L. So put these 2 equations that we have found earlier. It says n equal to mi plus 1, and also it says n is equal to L plus I. Now in this equation, see m is already here and n is already here. So m, the one that we want to find, so you can find the value of I from this equation. So we can say since n is equal to m plus I plus 1, then in here we will say that n minus 1 is equal to mi, and from here we say that I is equal to n minus 1 over m, and we have found the first equation. For the number of leaves, we have the number of leaves in this equation L. Here we don't have L, so let us start with this equation. And then here we will say since n is equal to L plus I, then we can say that L is equal to n minus I. So this equation, it has n, but it does not have m. It is expressed with I, so I have to find an equation that replaces I and it has m and n. So notice here that it has n and m, and this is I, so we will substitute I by this equation. So we will say that this is equal to n minus 1 over m. So therefore n is equal to, now we unify the denominator, so here we will have m, and here we will have nm minus n plus 1. Now take n as common, so we will have m minus 1 multiplied by n plus 1 over m, and this is the equation that we are looking for, number of leaves. For the second part, m is given and I is given. We need to find an equation for n and we need to find an equation of L. So m is given and I are given. Find n and L. Okay, just put those 2 equations in front of you. So n is equal to mi plus 1 and n is equal to L plus I. This equation, we have already found it by counting. Now for the second equation, how to find L? We will find L from this equation. So L is here is equal to, since N is equal to L plus I, so L is equal to N minus I. Now this equation, it has I, but it does not have M, it has N. So what we will do, we will put the equation for N and substitute it in this equation. So we will continue and we will say that L is equal to M-I plus 1 minus I. Why? Because N is equal to this equation, so remove N and replace it by M-I plus 1. So therefore, if you take now I common between these two, so you will have L is equal to M minus 1 multiplied by I plus 1, and this gives us the equation for L. For the last part, I will leave it as an exercise that you can try by yourself. For this theorem, we have a complete and full M-ary tree of height h. We need to prove that the number of vertices is equal to this equation. And this equation, it has two parameters. One is m, and the other one is the height. To find a proof for this theorem, we are going to use counting technique. Imagine you have the following full M-ary tree. So for every internal vertex, we have exactly m children. So we will count the children in each level. So here we assume that we have, this is level 0. So this is level 0. And this is going to be level 1. And this is going to be level 1. And this is going to be level 2. And etc. For the last one, we are going to have, this is just for demonstration, so it continues. So this is level 3. Now on the other side, we are going to count number of vertices in each level. Now for the first level, which is level 0, we have only one vertex, which is the root. Now for the second level, if you want to count how many of these vertices, in fact, they are number of children of m. And since this one, the level which is before is m, so number of children is m, so here we have m children. Now for each of these m children has also another m children. So here we have 1, 2, 3 up to m, and each of them has m children. So for level 2, we will have m square. And for level 3, for each parent, we are going to count, because we want to count number of these children. So how many parents do we have on top level? We have m square. For each of these m square, how many children do they have? So they have m multiplied by m square. This will continue. So if we have a height that is h, so what is the equation that we are going to get? So here we will write that n is equal to 1 plus m plus m square, and this keeps continuing until we reach level h. And this is a summation that it starts from 0, it goes up to h, m raised to power k. Because this one we assume that m is raised to power 0. This is a geometric sequence, but it starts with 0. So we can simply plug the equation we have for here into the geometric sequence. Let me write the geometric sequence for you to see it in front of you. We have summation k equals 0. It goes up to, let's say, n minus 1. And here we have r raised to power k. And this is equal to rn minus 1 over r minus 1. Now if you match this summation with this summation, both starts with 0. But this one ends at n minus 1 and this ends at h. So how did we get r raised to power n? So see, you are adding 1 to get n. So what you have to do for this geometric sequence, just simply add 1. So this will be equal to m raised to power h plus 1 minus 1 over m minus 1. And this is the equation that we are looking for. So for this example, in the first part, it says how many vertices, so n is required, and how many edges, which is e, does a full 5 array tree with 100 internal vertices have. So here we have m is equal to 5, and we have I is equal to 100. Now we need to know n, and since this is full, so remember the equation, it says M-ary plus 1. So from here, n is equal to 5 times 100 plus 1. So this is equal to 501. And you know, since this is a tree, so the number of edges is equal to n minus 1. So we will have 501 minus 1. So we have 500 edges. And here 501 vertices. For number 2, it says also how many edges does a full binary tree. So since it's binary, so m is equal to 2. And number of internal vertices is 100. So again, we can find number of vertices, which is mi plus 1. So here we have 2 times 100 plus 1. So we have 201 vertex. And number of edges is equal to n minus 1. So it's equal to 201 minus 1, which is equal to 200 edges. For the last example, it is required to find number of leaves, which is L, for a full 3 array tree with 100 vertices. So we have m is equal to 3, and we have n is equal to 100. So we have the equation n equal to mi plus 1. So from here, we have 100 equal to 3i plus 1. So how to find I? I is equal to 100 minus 1 over 3, which is 99 over 3 is equal to 100. Since number of vertices is equal to number of leaves plus number of internal vertices, so number of leaves is equal to n minus I. So we have found I, so we have 100 vertices minus 100, and this is equal to 89 leaf. By this example, we have reached the end of the lecture. So good luck and see you in the next lecture.